So today we will start the chapter Work, Energy and Power. Now what is work? It is a phenomenon that is associated whenever one form of energy is converted to another. So I have given you a definition for work. In order to derive work mathematically, what is the expression of work mathematically? Let me first define another important quantity, that is kinetic energy. Now what is kinetic energy? It is the energy possessed by a body mass due to its speed. And right now we are talking about point mass. Till we get to rigid body dynamics, we'll be talking about point masses. So I can write kinetic energy as half mv square, right? To be more precise, I can write this as let me differentiate both sides with respect to time. dk by dt is half into m. You can find out this becomes 2 times of v dot a. So dk by dt becomes ma dot v. So dk by dt becomes f net dot v. So dk by dt becomes, if I take dt to the other side, if you remember, we wrote dr by dt as v. So dr is equal to v dt. I am substituting this. So I can say dk is equal to now, since this is change in kinetic energy, and I told you whenever there is change in kinetic energy, the phenomenon of work will be associated. So I can say the expression of work will be related to this quantity then, right? So now I am in a position to define work mathematically because I have already defined it in words. So now how can I define work? Small amount of work done, dw, can be written as f dot dr, right? Where you know through dot product this can be written as f dr cos theta, right? So work done depends on Number 1, magnitude of force. Number 2, displacement. Magnitude of point of application. Angle between force applied and displacement of point of application. So these are the 3 things. Remember, we are right now talking about small work done. Right? Now, why I am stressing on this point, that displacement of point of application or magnitude of displacement of point of application. Please try to understand. Suppose I have a hinge. Suppose I have a hinged rod which is in vertical plane and released from rest. Say it goes to this position. If I ask you what is the work done by hinge, say finding out force of hinge is a phenomenon that we discuss later on in rotational mechanics. But here I can directly give the answer. That answer is 0, because no matter what force is applied by hinge, but it will be applied at this point of application. And this point of application does not move. So displacement of this point of application is 0. And hence work done by hinge force on the body or on the rod is 0. As we go into the chapter of rotational mechanics, I will discuss in detail how to find out this hinge forces at certain given instance. Okay. You also have to remember that work done, since it's a dot product of F dot dr, work done is a scalar quantity. Depending upon theta, it can be positive or negative. Okay. Unit is joule. SI unit is joule. Now we'll try to understand how do we calculate work done. We have this basic expression with us. So if I integrate both sides, I will get this, right? If this is the condition, case 1, when force is constant, if force is constant, I can take F out of integration. It gives me this. I can then write it like this. Right? That can also be written in Cartesian form like this. We know in dot product I cap gets multiplied with I cap, j cap with j cap, k cap with k cap. So this is the process when force is a constant. Okay. What shall we do when force is variable? What shall we do when force is variable? If force is variable, we cannot take F out of integration. So in Cartesian form, we can say F can be written like this in components. So work done then will be in Cartesian form, it's like this. So it can be written like this. Now if you pay attention, this is also area under fxx graph. This is area under fyy graph. This is area under fz z graph. Right? So if you want, you can calculate it graphically. If you want, you can do that by integration, depending upon how the equation has been given to us. Right? Okay. Let's solve some questions based on the conditions we have discussed till now. So let's take up this question. In this question, we first see the force given and we find out that the force is constant. Now if the force is constant, we know we are going to use this form. We also know that force is So delta R will be R final minus R initial. So delta R will be now work done can be written as F dot delta R. If I put the values, we know in dot product I cap gets multiplied with I cap, J cap with J cap, and K cap with K cap. So 3 into 2, that is 6, 4 into 3, that is 12, 5 into 1, that is 5. So work done turns out to be 23 joules. Our answer then will be option C. Another question. Let's take this for an example. Another thing that we should mark here is, right, say this should have been force in I direction and work done in moving the object from x equal to 0 to x equal to 3a. Okay. Now first thing, look at the force. As you go on changing x, force will change. So now force is a variable. Now if force is a variable, I know we are going to utilize this form. In this case, we have only x component. So can I say we are only going to deal with this part, the other two being 0. If I put the values, the limits are from 0 to 3a. It has been told to you that alpha is a positive constant. I can take alpha out of integration. If I do the integration, x dx will give me x square by 2. Dx will give me x. It is from 0 to 3a. Work done then will be and when I put 0 as limits, it will be 0 minus 0. It will be that should match with option A. So the only thing is you need to see the force, whether it's variable or constant, apply the formula, get the result. Let's see one graphical approach as well. So if we look at this question, we'll find out that the body is moving under the influence of a force that has two components, Fx and Fy, and their variation with x and y is given. If I utilize the formula, in our case we have x component and y component, but there is no z component. So this part is going to be 0. Now I can write this as area under fx versus x curve, and this as area under fy versus y curve. Let us calculate these areas. This area will be half into base into height, so this will be 3. Area of this square will be 2 into 2, that is 4. Area of this rectangle will be 2 into 4, that is 8. Now as we know, area above will be positive, below will be negative. So for the first term it will be 3 minus 4, and for the second it will be plus 8. Right? 3 positive, 4 negative, 8 positive. We'll get the total work done as 7, and as we know, unit will be joules. Right? Unit is joules. Hence the answer to this question will be C. Right? If nothing is given, we assume everything is in SI units. So this was in meters and these were in newtons. Right? So this is the graphical approach. So I hope till this much everybody is clear, right?